All right, well, welcome to the afternoon session and to the first invited talk of the conference. So, the speaker is Giulio Chiribella, and as you can see on the slide, he's from University, and he's going to speak about systems interacting with the environment.
Thank you very much. Well, first of all, I would like to start by thanking the organizer for giving me the opportunity to present our work in this beautiful venue and in this beautiful city of the country. So today I will talk broadly about the dilation theorems, but from a point of view of foundations. So not as mathematical theorems in quantum mechanics, but as ways to retrieve quantum mechanics from basic axioms. So let me start by giving a few credits. So this is mostly work in collaboration with Mauro D'Ariano and Paolo Perinotti. But today we'll also talk about things that I've been doing more recently with my group in Beijing, so in particular with Xiao Yuan and Carlo Maria Scandalo, typical Chinese student that you would find in Beijing. This work is supported by FQXI and by a program of the Chinese government for recruiting foreign experts. Okay, so what is the plan of the talk? So I will start with a little bit of an introduction on the puzzling core of the mathematics of quantum theory. So, of course, everyone has his own opinion, but in my opinion, the core of quantum theory is in a set of theorems that are called the dilation theorems. And I will start talking about this. Then the step after that will be to try to transform these dilation theorems, to export them, and to bring them to the framework of general probabilistic theories. So we want to talk about dilation theorems without having quantum mechanics from the beginning. So I will need, of course, to establish a framework. This framework has been hinted to already by some talks today, in particular the one by Bob Cook and Ray Dahl. And in this framework, I will start talking about this axiomatic approach to dilation theorems. So we'll talk first about purification, and then about a more recent set of axioms that I generically refer to as sharpness. And of course, I will give conclusions in the end. So let's start from the kind of broad motivating question. So what we want here, I think, is a goal, partly a goal of this community, is the one to understand better the origin of quantum mechanics, first of all, to ask why nature is obeying to this particular set of mathematical laws. And the other reason is to learn to think about quantum mechanics, to think in the mathematical sense, to make logical derivations from principles and to construct protocols from the principles in a direct way. So this was highlighted in a kind of broad sense in an article by Wheeler on the New York Times. And the broad question is, how come the quantum truth? So it's like quantum theory is a theory with an extremely broad applicability spectrum, but we don't really know what is the origin of such a successful framework. So jumping from the New York Times to sister algebras, so what is the core? If we had to say what is the core of this puzzling theory of quantum mechanics, well, I would say that the core is given by a set of theorems that are known as dilation theorems. And I think you're all familiar with them. So one is called, in its full generality, is called the GNS construction. So this is, in the simple case of finite dimensional systems, this is saying that every mixed state that you can find in quantum mechanics, every density matrix, is the marginal of some pure state of a composite system. So this is the result for states. There is another analog theorem for evolutions. In this form, it is due to Krauss. You may know it also as Stein-Spring theorem, but this particular form is due to Krauss. And the theorem says that whenever you have a noisy channel, whenever you have an evolution in quantum mechanics, you can always reduce this to a reversible evolution, so a unitary in the Hilbert space framework, a unitary evolution where the system interacts with the environment. Then there is also a theorem in the spirit in the case of measurements. So this theorem is due to Professor Ozawa, who is actually here with us, and it says that every measurement, technically every instrument in quantum mechanics, can be reduced to a reversible interaction, so to a unitary interaction of the system with the environment, here the probe, and this is followed by a sharp measurement on the probe, so by a projective measurement on the probe. So these are three mathematical theorems. They are consequences of the mathematical framework of quantum mechanics. The game that I will play here is to start to regard them as operational statements, not only as mathematical theorems, but as features that we would like to be true in any physical theory. Because I think there is a deep meaning that is attached to these theorems that essentially suggests that all the things that we see in information theory, all the mixed states that represent information sources, the noisy channels that we use to model communication, all these things can have an underlying physical picture that come where we can simulate the information processing as a sort of fundamentally pure and reversible evolution, or pure and reversible and sharp evolution. So I wanted to give some substance to this kind of intuition, and to do that I will need a framework. So I want to make these theorems into operational statements that hold without the framework of Hilbert spaces. So this goal is strictly close to the goal that has been pushed by some people here in the categorical sense. So this is part of what categorical quantum mechanics is doing. So probably the closest relative to our approach is the one by Selinger's CPM construction. So it's a way to have an abstract notion of completely positive maps and mixed states from purely categorical notions. And actually a way to understand the construction of the CPM construction in terms of interaction with the environment was presented by Bob Cook also with Simon Perpritz in other works, probably presented at QPL a few years ago. So what I'm talking about is a very close relative of this type of endeavor, of trying to understand systematically quantum protocols based on some abstract formalism that is more general than the Hilbert space formula. That's the general goal. So now I will give you our own way to do it. So the framework is slightly different from the one that maybe you are used to. So the framework is the framework of operational probabilistic theories. Roughly speaking, you can think of them as general probabilistic theories. I like to call them in this way because it's clear what are the ingredients that we are throwing into this framework. So I say operational hyphen probabilistic because this is a framework based on two distinct ingredients and on the interaction between them. So it will be a little bit informal and a little bit quick on this because I try to get to the point as soon as possible, but please stop me if anything is not clear enough or if you want more detail. So let's start from the first ingredient in our framework. This is the operational structure. So this is just the structure of what can be done in a laboratory. So we have a kind of abstract framework for experiments that are done in a laboratory. So the idea is that we have physical systems like A, B, C, D, and whatever, and we have tests that are things that we can do in the lab. So among the systems there is a special one that is the trivial system that just represents something that we don't describe, so like nothing in the laboratory. And then we have tests. So a test represents one use of one physical device. So this test will have an input system A, an output system A prime, and associated to this test there will be a set of possible outcomes in general. So our device can give outcomes. So there will be an outcome I in some outcome set, and there will be a list of possible processes that can take place. Each process is labeled by one outcome. So here you can really think of like a Stern-Gerlach device where there are two outcomes, let's say 0 and 1, and outcome 0 means that the system goes up in the trajectory, and outcome 1 means it goes down. So there are two processes that correspond to two different outcomes that you can read out on the display of your device. This was actually mentioned already by Ray in his talk today, and I will also go pretty quickly on that. One thing that you need to notice is that every test, every device, by having an input and an output, is a directed object. So there is an input-output arrow, in my convention is from left to right, that gives a direction to these devices. Okay, so what we can, there are special cases of devices. There are devices with a trivial input, so we call them preparations, and the particular preparations are states. So the particular things that can happen when you prepare a system is that you prepare different states. And also there are tests that have trivial output, so they are demolition measurements, where we destroy the system, and for every outcome there is one way to destroy the system that is called effect. It's just to fix the language and make sure that we are all on the same page. So what we can do with these devices is to build up circuits. Of course, there is a lot of formal properties that one has to require for circuits. I will not go into that. We all know what are the formal properties because we are used at least to quantum circuits. So these circuits that I draw here are the analog of quantum circuits, but just without Hilbert spaces. And for many of you, this will ring a bell, because these circuits, mathematically, are described by the graphical language of symmetric strict monoidal categories, as Bob mentioned today in his talk. So in particular, this language was developed by the QPL community, starting from Avransky and Cook, and also was developed in Cook process theories. As we heard today, there is a book that is going to come out on this, and also in the survey and the works by Selinger on graphical languages. So what I'm using here is exactly that mathematical structure. So the tests I talk about form a strict symmetric monoidal category, and the particular processes that can take place when we do the experiments also form strict symmetric monoidal categories. So I'm breezing on this, but keep in mind that the mathematical structure is the mathematical structure of monoidal categories. That's all about the operational structure. So what I call operational is the purely graphical representation of circuits, of the things that we can do in the lab. So the framework comes from the marriage of the operational aspect with the probabilistic structure. So we had in mind that we want to introduce quantum mechanics as a physical theory that gives predictions about experiments. So we wanted these circuits to have probabilities. We want to talk about the probabilities of outcomes. To do that, we have to add one ingredient on top of the operational structure, and we do it in the easiest possible way. We just stipulate that when we combine a preparation with a measurement, we get a probability distribution of the outcomes. So notice that this is a joint probability distribution. It's the probability that the preparation is I, and rho I, and that the outcome of the measurement is J. So this is a joint probability distribution. We axiomatically require that each probability is positive, and that we have normalization when we sum over all outcomes of the preparation and all outcomes of the measurement. Okay? So this is the probabilistic structure that we put on top of the circuits, and we ask this structure to be compatible with the structure of the circuits. So if two circuits are equivalent in terms of equivalences within the category, they should also give the same probability. So circuits that look the same should have the same probability. Also, there is one request that one needs to ask. So we need to ask that if we perform two experiments in parallel, then the probability distribution for these two experiments is uncorrelated, is factorized. So it's nice here, you can see really the correspondence between the graphical language and the probabilistic structure. Here we are asking that what is factorized at the graphical level should be a product at the numeric level of probabilities. So you can think here of the role of two dice as the example of two experiments done in parallel. So you expect that the probability is the product if you roll two dice. That's it. Essentially, that's the whole thing about the framework. The framework is just a framework where we have a circuit model and we have a notion of probability of outcomes in the usual sense. Probability as a positive real number. So this may sound little, but there is a lot we can do with it. So let me summarize. So an operational probabilistic theory for me means this. It means the sum of an operational structure plus a probabilistic structure. And this is surely very broad. You can put here classical theory, quantum theory. You can put quantum theory on real Hilbert spaces. You can put quantum theory with restrictions. For instance, you can imagine a theory where you have all possible quantum states, but the operations that you can do are only the LOCC operations, like the ones you can do by local quantum operations and classical communication. This is a theory, and you may want to describe it as an example of this general framework. So you can stick many things inside of the framework, and and with this little structure, there is already a lot that we can do, a lot that we can squeeze out of this combination of circuits and probabilities. The first thing we can do is to take a quotient. So we can say that two processes, let's say Ci and Dj, are statistically equivalent if there is no way to distinguish between them in any possible experiment that you can do in the theory. So you cannot distinguish between these two processes from the probabilities of experiments that you can run. So imagine that you prepare any possible state, even of some correlated composite system, and you apply one process. And after that, you perform a measurement. So if you get the same probability by exchanging this process with the other process, then the two processes are equivalent. So in quantum mechanics, this is already taken care of by the formalism. When we say that a quantum process is described by a particular completely positive map, it means that we have already taken this quotient. I mean, we don't distinguish between a completely positive map that describes a device painted red from the same completely positive map describing a device painted blue. I mean, we don't care that the actual device in the lab was red or blue. We care only about the probabilities of the outcomes. And if we are so general that we start from circuits and probability, we have to take a quotient here. So if you take a quotient, you get a new operational probabilistic theory that is kind of is less redundant, is more useful. So from now on, I will care only about theories that are a quotient of some original theory. So if you do the quotient, you have a lot of structure already. So you can prove a theorem that just by definition, just by the fact that you had circuits and probabilities, you get for free a structure of vector space. So every process with a given input, A, and with a given output, A prime, can be embedded as an element of a real vector space. So that the processes of a certain type, in every possible theory, are elements of some vector space. And this comes for free without any assumption of convexity whatsoever, just from the fact that we have circuits and real positive valued probabilities. No extra assumption is used here. Another thing that you get for free is that the sequential composition of two devices is linear, is a linear map, is a linear mapping in both arguments. So if you take a linear combination of processes here, and you can do this because they are elements of a vector space, and you compose this with a linear combination of processes there, then you obtain a composition that is bilinear, that is linear in both arguments. Also this comes for free, just from the definition of the framework. So in particular, this tells you that states of a given system can be thought as linear functionals over the measurements, and measurements can be thought as linear functionals over the states. because you can put the measurement here and you have linearity in the state. You can put the state here, you get linearity in the measurement. Yes?
Can you allow multiply by negative number?
Oh yeah, sure. I mean, this is a mathematical construction that we are putting on top of of our framework. So we could even put complex numbers if we wanted. For the purposes of what I want to do, I'm happy to keep real numbers, but yes, we can put negative numbers as well. They don't have a particular physical interpretation, but they are there. They are in the vector space. So they are.
But then your state changes to the positive state.
Sure. I mean, there will be states. States are elements of a vector space. And then we can take linear combination of states, and we will obtain things that are not states anymore. They are just elements of the vector space. Like in quantum mechanics, we have the set of density matrices, trace one, positive Hermitian matrices, and we can take the linear span of these. This will give the vector space of Hermitian matrices. If we take all possible linear combinations. So you can imagine here for states, the vector space I talk about is the vector space of Hermitian matrices on a given complex space. Not every matrix is a state, but the states live in this vector space. Okay, so this is just to say that we get a lot of structure for free just from the fact that we have circuits married with probabilities. So what we can do now, an easy thing, is to define pure and mixed processes. We can say that a process is mixed if we can obtain it as a sum, as a coarse graining, over processes coming from a more refined test. So in this case, this would mean that the ignorance, when we have a mixed process, we have some ignorance about what is really happening in the lab. And by contrary, you can say that the process is pure if there is no way to write it as a sum over processes, except in trivial ways. You can think that we randomize the preparation of the same pure state, but except for trivial linear combinations, when we have a pure process, we cannot have anything else, only trivial combinations. So if you take this general definition in quantum theory, it gives you what you want it to give. So if you take this definition, a mixed state in quantum theory is really a density matrix, and the pure state would be a rank 1 projector. Notice again that I didn't ask any convexity here. Linearity does not come from convexity, despite what is often said in many occasions. Linearity comes from the definition of the framework. It doesn't come from the fact that the states form a convex set, which may not be the case even. Yes?
Is convexity just implicit that we assume probabilities?
No, we could have a theory that has some probabilities but doesn't allow for convex combination. I mean, it would be a restricted theory, but we could have instead. We could have a theory of the experimenter that is tied to his desk and can only get one particular process but no complex combinations. You may ask why we would do that, but in principle we could. The framework is general enough to do even that. So anyways, the point of my slides here is that linearity, the notion of pure and mixed, they don't come from convexity, they just come from the framework. Okay, that was it about the framework. So now I will start playing with axioms. So I will define a few axioms that they will be like the colors that we use to paint our picture of what quantum theory is. So the first axiom is causality, and thanks to Bob, I don't need to talk too much about that because this was very beautifully reviewed already this morning. So let me go a little quick on that. So causality, if you just say in plain words, in plain English, is the requirement that the choice of test that you will do in the future cannot affect the probability of measurements that you are doing now. Okay, so the probability of an outcome now should not depend on the choice of experiments that you will do tomorrow. So this is what we call causality in kind of plain words. Technically, it means this equation. So whenever you have two measurements, two possible measurements on the same system, and you put the same preparation, so you have some random preparation of state that prepare a state rho I, some set of states, and then you perform the measurement. If you sum over all the outcomes of the measurements, the probability that you get, the marginal probability distribution, should not depend on the choice of measurement. And so this probability distribution should be interpreted as the probability of the preparation, of preparing rho I, irrespectively of what measurement you will do tomorrow. So the probability that you prepare rho I today should be independent on what you measure tomorrow. So this is the formal statement of what the causality axiom is in this framework. Is this clear to everyone? So you can think of this as no signaling, because as I told you, this diagram represents a joint probability distribution. So this is the probability distribution of preparing rho I and getting the outcome J. So it's a joint probability. You are asking that the marginal does not depend on which measurement setting you choose. So this is a sort of no signaling, and I will elaborate more on that. So equivalently, if you just, since this is for every state, you can take out the states on both sides. What we are really saying here is that if we sum over all possible outcomes of a measurement, we get a result, we get an effect that doesn't depend on the choice of measurement. So this is the unique deterministic effect that we have in our theory. So causality is the statement that there is only one deterministic way to destroy a system. And this was the effect that Bob denoted with these 3 lines, this kind of stop line for systems this morning. So you get a very easy result from this, from the fact that you have a unique deterministic effect. You have the fact that there is only one way to destroy one system, only one way to discard a system. So there is only one way to define the marginal of a bipartite state. So if I have a state rho AB of 2 systems together, the marginal on system A is just what I get by applying the deterministic effect on system B. Since there is only one deterministic way to throw the system B away, the marginal is defined in a unique, well-defined way. So in quantum mechanics, just to make sure we are on the same page, in quantum mechanics, the deterministic effect is the trace. So when we write this diagram, rho with the deterministic effect, we mean the trace of rho, when rho is in a matrix. So the marginal is just the partial trace, the usual notion of marginal in quantum mechanics. So from the fact that the marginal state is unique, you get immediately no signaling from the probability distributions. So whenever you have Alice and Bob that are making local measurements on bipartite states, the fact that the probability distributions that they get in this way are no signaling is just an incarnation of the fact that we have causality. Because if we sum over all possible outcomes on Bob's side, we get something that depends only on the deterministic effect. So this point was very well highlighted by Bob this morning in the talk. So what he had in the talk was the abstract elaboration of this idea without real valued probabilities. That's the big difference between what you have seen in the morning and what I'm talking about now. But conceptually it's the same point that we are making. So that the causality at the level of one system implies no signaling at the level of multiple systems. Actually, not only implies, it's equivalent to. The other thing is that, as I said, causality can be thought, the equation of causality can be thought as an equation of no signaling from the future. So we are saying that the things that we do in the future cannot affect, cannot signal on probability distribution of what we do in the past. So this is a negative way to describe causality. There is also the positive way. So whenever you have causality, you can use the information that you have in the present to choose what you will do in the future. So this is the feed-forward version of causality. So in a theory that is causal, you can always decide to choose tomorrow to perform a test that depends on the outcome of a test that you had today. So this is like a feed-forward from the past. So this is actually a slightly stronger condition than causality, but morally they are the same. I don't want to enter in hairy distinctions, but this thing is slightly stronger than causality. And this is probably one of the most important aspects of causality. Why is it important to live in a causal world is because in this way we can learn from the past to decide what we will do in the future. So much for causality. So I need causality to state the axiom I care about. So the axiom I care about really is purification. So this is a much more non-trivial axiom. and the way I phrase it requires causality. So the informal statement of purification is that every mixed state, every state of ignorance that you can find in your theory, can be modeled as the marginal of a pure state, of a pure bipartite state, in an essentially unique way. So this is informally is telling you that whenever you are ignorant, you can justify yourself and say that actually you have to be ignorant because your system is perfectly correlated with another system that we are not describing here. So it's like a student who was asked a question about mathematics and he didn't have any answer. He would say to the teacher, well, if you asked me a question about mathematics and physics together, I would have the perfect answer to give you, but you asked me only one subject, and then I look ignorant, but it's not really my fault because of that. So if we make this more formal, so we can break down the statement into graphical equations. One is the existence of a purification. So we're saying that for every mixed state rho, for every state in general, there is some pure state psi of two systems together, such that the marginal of psi on system A is the original mixed state rho. You can see here why I bothered explaining causality, because we have to talk about the marginal of this bipartite state. So I need a canonical way to talk about the marginal here. So this is the existence of the purification. This is the axiom that allows the student to justify himself and say, well, actually, about A and B, I knew perfectly what was the state. The other thing is the uniqueness. So whenever we try to make a model of the world based on our partial information, we would like this model to be unique in some sense. We would like to say that when we do physics, when we try to represent things in terms only of pure states, there is an almost unique way to do it given what we know about our system. So what I'm saying here is that if we have two different pure states with the same marginal, so if we have two purifications of the same state, then these two states should be equivalent up to reversible transformations on the purifying system. So I think you are all very familiar with this property from the Hilbert space formalism. Now I'm promoting this property to an axiom, to something that I want to be true. Now I'm looking at this as a positive thing that I want to happen in a theory. Yes? It is.
Some extra PS and purification with this additional.
Oh yes, but the system is the same. We should notice that there is B and B. So whenever you have two purifications, even that entangle A in the small subspace of B, you can always rotate the whole system B in a way that you convert one purification in the other. So this is purely reversible. It's really unitary in the Hilbert space form. That's actually a very good question because this is something I should have highlighted. The system, the purifying system here is the same. So I'm asking only properties of purifications with the same purifying system. If the purifying system is different, we can say something else, but it's not part of the axiom. So what we can say for different purifying systems is a theorem that we can prove. But the axiom is only about the same purifying system. Morally, this means that when I am a theoretical physicist who observes the incomplete data in the lab, I want to work out a pure model of the universe where I say that I pretend that I understand what is the physics going on, and I want my model to be essentially the same up to a change of basis in the environment. So whenever you fix the environment, the model is essentially unique. So this is what you would like as a theoretical physicist, or I would like at least. Okay, so this is the axiom, and now I will give you a bunch of consequences. So just assuming purification, and of course causality, because we need causality to talk about purification, we get a host of properties of quantum theory and quantum properties. I mean, probably more than you would have imagined. So one easy thing, one obvious thing, is entanglement. So whenever we start from a mixed state, a state that is not pure, then the purification has to be entangled. There is no way. You can see it's a trivial consequence. If it were a product, if the purification were a product, also it had to be a product of pure states, and then the original state would have been pure too. So what is this telling to us? This is a trivial statement by itself, but it says something trivial. It says that every theory where we do have some mixed state will have entanglement. So there are only two possibilities in life. One is that you have a theory without mixed states, so like a completely deterministic theory, where every measurement will give an outcome with probability 0 or 1, or you have a theory with entanglement, if you require purification. So essentially it's like either deterministic or entangled. Of course, I care about the case where we have mixed states. So from now on, I assume that we are talking about theories where actually you can make mixtures of states. So another easy consequence is about single systems. So you can prove that every pure state of a given system A can be connected with every other state by some reversible transformation. So this is just a particular application of the uniqueness of purification. So this means that morally all pure states have the same status in your theory. You can transform one into the other just by some reversible change of reference frame. Something that you get from this is the fact that for every system there is a unique invariant state. So this state is the state identity over D in quantum mechanics, quantum theory. So the fact that you have that every pure state is equivalent to every other state gives you the fact that you have a unique state that is invariant. And this state is very handy when you want to prove theorems, because it has very nice properties. Okay, from this, you can also, from purification, you can prove also a property known as steering. So whenever you have an ensemble of states, rho I, so that the average of the ensemble is a state rho. So you can imagine this is an information source that splits systems in some states, and you take the average state of this source. Whenever you have such a source, you can purify the average state of the source, and you can induce every state in the source by making a measurement on the purifying system. So this property was noted by Schrödinger already in 1935, and it came up recently again in quantum foundations in the work of Niels Barnum with the word steering. Steering is also useful because it allows you to do process tomography. So if you take the maximum, the invariant state, the state chi that I showed before, and you purify it, so every purification of that state is going to be useful for process tomography. In the sense that if you have two processes that do the same on that particular state, then the two processes are going to be the same. So this also appeared, this is a reminiscent of the Choi-Yamaoka isomorphism in quantum theory, and also of what it was called the name of a process in the categorical framework. I think this is so there is a way to get this structure from categorical axioms as well. One thing that you can get from this, that is pretty getting towards quantum information, is no information without disturbance. So imagine that you have a test where you test system A, and for every possible outcome of your test, you will transform the system with some process Ci. Now you would like not to disturb the state of the system, so you would like to sum over all possible outcomes of your test, and you would like to have something that doesn't disturb the state. So which means that what you are doing should be the identity on your system. So this condition is a condition of no disturbance. So if you have a test that is non-disturbing, then you can easily show that each process is proportional to the identity. So it means that you are not doing anything, essentially. The only thing that your test is doing is to toss a coin, get an outcome I with some probability, pi, that is totally independent on the state, and just do nothing on the input state. So essentially from purification, from the fact that you can purify your ignorance, you get the fact that the identity is indecomposable. You cannot break the identity into smaller pieces. The identity is a pure process in quantum theory, which is very different from what happens in classical theory, where you can break down the identity into processes. From no information without disturbance, you go directly with to no cloning. The proof is 3 lines. So if you had a perfect cloning machine that can clone every pure state, let's say, then you could, it's easy to show that this machine would allow you to make a perfect discrimination of all these states together. So you would be able to distinguish pure states among themselves. But if this were true, you would have a test that doesn't disturb the system. Because you trying to distinguish the pure states, you could measure on the pure state, and depending on what you get, you could re-prepare the same pure state. So this procedure would not disturb your state, and on the other hand, it will identify your states. So it will be a non-disturbing state, a non-disturbing test that has non-trivial information. So this would violate the no information without disturbance principle that we have just gotten from purification. So you get no cloning from purification. The other thing that you can get is teleportation. Teleportation essentially is an application of steering. So once you have steering, you get to teleport. You can construct by hand a teleportation protocol. So what you can show is that you can always find some measurement. This would be the Bell measurement in quantum mechanics. There is some measurement so that when you apply this measurement on a system and on half of an entangled state, this diagram will send you the state from the input here to the output there. So this will be a teleportation experiment that you can construct directly from purification. So this thing is also a very characteristic thing that appears in the categorical framework. But remember that here we have vector spaces, so we have actual numbers, so we can do some computation. So for instance, we can find a bound on the probability of successful teleportation. And the bound tells you that the probability that you teleport a state is the inverse of the dimension of the vector space generated by the states. So remember, we had this discussion before. So in quantum mechanics, the vector space of states is the vector space of Hermitian matrices, of d by d Hermitian matrices. So this thing is d squared. So in quantum mechanics, this bound is 1 over d squared, which happens to be the exact bound that is saturated by the original teleportation protocol. You can construct many other protocols in quantum mechanics that don't saturate the bound, but the original one actually did saturate. Okay, so the other important point is that from purification you can get to the dilation of noisy processes. So remember that this was essentially the motivation, the starting point, the intuition that guided our work. So now we can prove a theorem, starting from the purification axiom, that says that whenever you have a noisy process, like a channel in information theory, you can realize this process by coupling the system with an environment. The environment is in a pure state. The coupling with the interaction between the system and the environment is a reversible evolution. And you just get the original noisy process by discarding the environment. So this is a kind of abstract version of Krauss' dilation theorem in quantum mechanics. So if you want to put it in plain words, this is telling us a sort of conservation of information principle, that in the pure world, information cannot be erased, it can only be discarded. You can always decide to forget about the environment, but actually the information will still be there, because everything up to that point was reversible. Another thing that we can do just from purification is to get to the operational version of Ozawa's theorem. So whenever we have a measurement process, we have some process with outcomes, we can model this as a reversible interaction with an environment, followed by a measurement on the environment. So also here we can have a kind of dynamical representation of every test that we have in our theory, just based on pure and reversible objects. I will come back to this also later. There is an immediate application, so this is not pure mathematics. So there are things that you can do with this. So by using Ozawa's theorem, once we have this operational version, you can prove a principle of delayed measurement. So if you have a sequence of tests, like measurements that you can have different measurements in time, you can purify each of them. And since you have the monoidal structure, you have commutativity of things that you do in parallel, you can bring all the measurements that we had in Ozawa's theorem to the end of the circuit. So we can imagine that everything we can do in these theories is actually equivalent to processing pure states with reversible interaction until the very last minute, where we make all the measurements that we had to do. For those of you who are familiar with cryptography, this is the working principle of the no-bit commitment proof. So we can also prove here that the protocol that is called bit commitment is impossible just due to purification. So for those of you who know, I mean, I'm not going to explain bit commitment here because it would require a little bit of time. For those who know, so what we prove here is that if a protocol is concealed, so if Bob cannot learn the value of the bit, then by purification it cannot be binding, which means that Alice can change the value of the bit until the very last minute. So this is essentially the same argument that was proposed by Lowe and Chow and Myers, and later was refined by Dariano and others, Werner and other authors. Okay, so much about purification. I want to use the last minutes available to talk about a more recent line of research that is following the same spirit. Actually, when I talked about Ozawa's theorem, you could have told me that I cheated, which I did. I cheated you. Because in Ozawa's theorem, there is not only the reversible dilation, but there is also something more. The measurement that we do in the end is a sharp. In quantum mechanics, this is a projective canonical measurement. The point is that until now, I didn't really have a definition of what was a sharp measurement, so that I couldn't even possibly prove the analog of the original theorem. So now I want to get closer to an actual analog of the theorem, so I need to define what I mean by a sharp measurement. So what is the analog of an observable, of a canonical observable in this framework? So there are possibly many possible definitions. So here I give you the one that we came up to, and I like it because it's kind of following the ideas that were already there in the quantum tradition. So it's kind of the natural definition that you would imagine if you came from the community of quantum foundations who worked on this in the past. So we say that a certain measurement, so this is a demolition measurement that we are doing. So a certain measurement is a sharp. If you can find a test, first of all, this test should give the original measurement as the probability rule. So you would like that the measurement that you start from can be implemented by this test, and this test gives also the state reduction. Okay? So you want to go from a demolition measurement to a non-demolition measurement. So you say that the demolition measurement MI is a sharp if there is some non-demolition measurement, some physical process that changes the state, so that the change of state corresponding to the outcome I has the probability given by this effect. And now you want this measurement to have some special feature. You would like it to be repeatable. So you want that if you apply the measurement process... Oh, sorry, I flipped. I realized this time. So every diagram should be flipped because these are measurements and not states. I'm sorry. But actually they are. Sorry, false alarm, nothing. So you would like that if you first perform the measurement with the state reduction, and after you perform the measurement MI, you would like to get the same result. So if you do the measurement twice, you would like to get twice the same result. And this is the repeatability condition that was actually analyzed by Luders in the very canonical or orthodox tradition of Hilbert space quantum mechanics. And the other condition is a condition of no disturbance. So if you have another measurement, Nj, that refines your original measurement, so suppose that your original measurement is a projector on some big subspace, and you want to refine this projector, you have a measurement that is more fine-grained, then the measurement process that we have here should not disturb this more refined measurement. So operationally, the idea here is that if you don't care about some information now, well, you can always care about it in the future, and you will find it there without disturbance in the end. So this is a condition of minimal disturbance, because these are like the only things that you can avoid to disturb are the states, are the measurements of this form. They're fine. Also, this was the canonical condition studied by Luders in his original work in Hilbert space quantum mechanics. So this is the definition. Any question about the actual definition of sharp measurement? properties. I mean, it's one out of many, many possible choices. We choose this because it's kind of following a tradition that was already there in quantum mechanics. So now we can, after we have a definition of sharp measurement, we can start putting axioms. So the number one axiom is that every measurement that is not sharp, so every measurement that is noisy, should come from some sharp measurement on the system together with the environment. So the philosophy is always the same. Whenever we have something that we don't like a mixed state or a noisy channel or a noisy measurement, then we add the environment and we turn it into something that we like. In this case, we turn it into a sharp measurement. So essentially here we are saying that in principle we can always claim that every measurement is fundamentally sharp. It's just that we are accidentally measuring some part of the environment that is not under control. Yes? Oh, that's a very good question. For the moment, we were not able to prove it, which doesn't mean it's independent, which means we were not able to reduce one to the other. Surely they express the same idea, but there is something slightly different because this sharpness condition is putting extra things there. So, but on face value, as far as I know, it could very well be independent. So there are another two axioms that are more auxiliary things. You can ask that whenever you have a sharp measurement and you coarse grain it, you still get a sharp measurement. So the intuition here is that if you coarse grain, you get a measurement that extracts less information, and you don't expect that you are going to make more disturbance if you extract less information. So essentially, your measurement should still have the nice properties of repeatability and non-disturbance that you had before. The other requirement is a locality requirement. It means that if there are Alice and Bob, and Alice performs her sharp measurement, Bob performs his sharp measurement, if you regard these two measurements as a measurement of a joint composite system, they are a sharp measurement on the joint system. So this is a very natural thing, but in principle, if you don't assume any other axiom, this is a request that you need to prove things. So what do we get from that? So we get something pretty interesting. We get bounds on the actual numerical values of correlations and of contextuality inequalities. So I will not explain to you what these things mean. So there is an active line of research on computing inequalities about quantum contextuality, like Kliatchkov's inequality, and of course there is an active line of research on computing bounds on Bell correlations. So from these three axioms, we actually get numerical bounds on the correlations. And these numerical bounds, for those who know, are given by this consistent exclusivity feature. So from the second axiom, we get consistent exclusivity. From the second and third, we get a hierarchy of consistent exclusivity conditions. And from the three axioms together, we get an axiom, a property of correlation that is called local orthogonality. If you don't know what they are, it doesn't really matter. They are just numerical properties of the probabilities that you find in quantum mechanics. Nothing even so fundamental to them. It's just that people like to see the numerical values, and it's kind of surprising that from axioms about pure processes, you actually get numbers. You get like square root of 5 minus 3 for a particular Kliatchkov inequality. So you get the actual value from the axioms. So until now, the philosophy has been we get protocols, we get features from purification-like axioms, from purification of states and from the sharpenization of measurements. So the question is, can we really make the punchline? And can we say that quantum theory, by definition, is the only possible theory where we can have this ideal picture by enlarging the description? So we don't really have that completely, but we have a result that is now a few years old that goes in that direction. So what we had was a sort of portrait of quantum mechanics as a physical theory of information. So let me just say what is the result, what is the message. So in our work we had a number of axioms, so not only purification, but a bunch of things. And these things are properties that are shared by classical and quantum theory. So they are kind of normal, innocuous, ordinary properties that you would expect to hold in a reasonable theory. I don't claim that these are the only properties you may ask, but surely there are things that you wouldn't consider strange. So we have these 5 features, plus purification, which is the big conceptual leap to get to quantum mechanics. And putting the two things together, we actually proved that quantum theory is the only possible model satisfying the axioms. So there is a mathematical proof essentially in a long PRA paper, proving that these 6 axioms together get you to quantum theory. Actually, I should say these 6 axioms plus the framework, because the framework contains a host of axioms by itself. So morally, what we have shown, so the take-home message of that result, was that quantum theory is the only pure and reversible theory of information. By which I mean that if we have here the world of physics, the world where we try to describe reality as a place where there are pure states, to describe perfectly well our systems, and we want to reduce every dynamic to a reversible one, as the string theorists, for instance, try to do. So if we have on one place physics, and on the other side we have information theory, which by definition is the theory of ignorance, so it's the theory where we cope with probability distributions, mixed states, and noisy channels. So actually these two worlds touch in only one point, and that at that very point is a quantum theory on complex Hilbert spaces. So put in another way, this kind of result is reminiscent of Schrödinger's quote about entanglement. So in the old paper he said, this thing that the best possible knowledge of a whole does not necessarily imply the best possible knowledge of the parts. You can argue that what he's talking here is the purification property of quantum mechanics. So you can have a pure states of two systems together, so the best possible knowledge of the whole, and you can still have a mixed margin, so you could have ignorance about the part. So later in the same paper, Schrödinger said this famous quote, he said that I would not call this property one, but rather the characteristic property of quantum theory. And somehow now we have a mathematical proof that this intuition was right. By the way, I like also from this quote the fact that he says, the one that enforces entire departure from classical lines of thought. I like to think as a way to synthesize the goal of what we are trying to do. I mean, not only we, but also this community. So we are trying to define the new lines of thought that come with quantum mechanics, which means we want to have high-level axioms that tell us how to make proofs and derivations just from first principles. With this I'm done, so the conclusion of this is, I wouldn't even read it. So it's that essentially the idea that you can go to a higher level of pure, reversible and sharp processes seems to be, in my opinion, the distinctive feature of quantum theory. I would take it as the definition of quantum theory. So you probably can see that there is still a lot of work to be done, especially on these ideas of sharpness, which we haven't explored yet in their full generality. So my dream now would be to have a proof, a new derivation of quantum theory, talking only about purification and sharpness, without even the other axioms in common with classical theory, and just say that quantum theory is what we get from that. And also there was this point of causality, so whether we can talk about purification without having causality. This is pretty exciting if we want to think about the space-time in a quantum way. And we have already some results on that, but of course there was no time to talk about these particular things, which are also a little bit under development now. So thank you very much for your attention, and I leave here some references for the things I talked about. Thank you.
Are there any questions? Yes, Paul?
So, assume you retain the causality postulate, but you allow your probabilities not to be probability, meaning they don't sum up to one. What do you break down?
So when you say they don't sum up to one, you mean that there is no notion of sum, or that they sum up to 5?
Yeah, they can sum up to 5.
Then I think...
Because then you sort of throw away half of what I call causality in a way.
I think if you do what you said, you would end up in the world of post-selected quantum theory. So this world where you can simulate time travels and pretend that they happen with the probability 1. Just because there is no notion really of probability, there is only a notion of possibility, like having probability different from 0. The only thing that matters at that point is whether the probability is 0 or some positive number. It's a pretty weird world. It's a world where we cannot really control the preparation of our state. Because if we are a little bit entanglement with an environment, the person who holds the environment can deterministically steer every possible state here, just by the fact that everything that is possible becomes somehow something that happens. What, in your comment that I'm throwing away, this would amount to throwing away half, I'm not sure I understood what you meant, but...
The way you say that there are two notions of causality, the causality axiom, and then the idea that the probability is out of one, which seem to be independent. One is for probabilistic sign, and the other one is an axiom, which you know. So there are actually two normalizations.
I see what you mean. So in a sense, there could be, I don't know if this is consistent, but one could have a theory where the deterministic effect, the one that stops everything, that one, actually doesn't give probability 1 to the normalized states, but gives probability plus infinity. So everything else can be stuck under this effect, and then you would end up with that world. So yes, I agree with that. So you could have a probability that normalizes to infinity in general, instead of 1, and then everything could stay together in the same process.
Are there any other questions? Yes?
I'm slightly confused about your statement of real linear space.
Oh yeah.
I understood that you thought that the set of the test becomes a linear space.
The process is actually. So a test.
So for example, your category has many models. For example, you consider the models, the category of instrument, very standard way.
Yes.
Then this test or process corresponds to instrument.
Yes.
But then an instrument can be make any negative multiplication because instrument is just becomes a convex set, which allow only the affine combination.
Sure. Yes.
Because of the conservation probability. But you talk about some negative multiplication of the instrument, but that cannot be inside this category by definition. Because that means that you are talking about category process, and the category of the instrument is a model of this theory. That means that your statement that the set of the all tests becomes linear algebra and linear space does not is not satisfied in this model.
And
So let's say that your statement cannot be proved from the general axioms.
No. So let me try to clarify this point. Actually, this is a very good point. Is a good example, the one of instruments to clarify this point of the vector space. So in quantum theory, we have instruments that they are collections, finite collections of quantum operations. In our examples, they are instruments with finite outcomes. Right? So each instrument is a collection of quantum operations. So what we are doing here is to generate a vector space by taking linear combinations of quantum operations. So we get a linear space of linear maps from density matrices, well, from matrices.
I understand, but then you should state that the linear space is generated by instrument, not the.
Sure.
Yeah, you should write that.
Well, yeah, I should write it in the slide.
No, you write that just the instrument forms, the set of the test forms the linear space.
I see what you mean. Yes,
No.
I use the word form to mean generate.
No.
Yeah.
That's not
Sure.
common sense.
Sure. So they are not a linear space themselves, but they are a spanning set for a linear space. Yeah.
Any other quick questions? No? Okay, then we will thank the speaker again. Thank you very much.